This is a continuation of section 2.1 in your text, still over matrix operations, but this one specifically on multiplication and transpose. Let's talk in more detail about matrix multiplication. So we've dealt with multiplication before. We were dealing with vectors, but you're going to find that this looks very familiar to you. So first of all, this is just the formal definition from your text. If A is an m by n matrix and B is an n by p matrix with columns B1, B2 through BP, the product AB is the m by p matrix whose columns are AB1, AB2, etc. Or that AB is equal to A times B1, B2, B3, which results in AB1, AB2, etc. through ABP. So you might be thinking, well, that didn't make any sense at all. So let me help you hopefully make sense of what all of that said. So the first thing I want to point out to you is that we have A that's an m by n matrix. So A is m by n. And then we have B that's an n by p matrix, n by p. And I want you to notice that n is the same as n. And that's very key. And again, we talked about this in our last chapter when we were dealing with vector multiplication, and we talked about matrix multiplication. If these values do not match with one another, then we cannot do that multiplication. So check your columns of A and rows of B, and if those two are equivalent, then we can multiply. The other thing that you should notice here is that the resulting matrix, AB, which is a product, is an m by p matrix, m by p. So that is the resulting matrix is going to be m by p. The other thing I want to point out, and this will be much more clear once we do an example together in just a moment, is that essentially what's happening is I'm taking A, which is a matrix, and I'm multiplying it by the columns of B. So essentially what I'm saying is B, however big or small it is made up of columns, which are kind of like vectors, and I'm taking A times each of those vectors, and that is going to be my result. So let's take a look at what this actually looks like. Let's take a look at an example together. I have matrix A, which is a 2 by 2 matrix. Again, 2 rows, 2 columns. I have matrix B, which is a 2 by 3 matrix, 2 rows, 3 columns. So the first thing I should do is ask myself, can I, in fact, multiply these together? Whoops, I got rid of my 2 by 2. And of course, I would check that these two values are the same, and in fact they are, which tells me that my resulting AB matrix is going to be 2 by 3. So this is going to be a 2 by 3 matrix. Now I've just written some other things in here from what we just learned in our last definition. So I know when I multiply A times B, I'm going to end up with A multiplied by each column vector that makes up matrix B. And my resulting matrix will be A times B1, A times B2, A times B3. And of course, that's our 3 columns. So we would get started by computing each of those values. So I'm going to take A times B1, and that's going to give me 4 times 0 plus 1 times negative 2. So I don't have room to write all of that out, and I don't expect you to on your homework. What I would like to see on your homework is 4 times 0 is 0. 1 times negative 2 is negative 2. So I know you're actually doing the work to compute these. And then 5 times 0 is 0, plus 2 times negative 2 is negative 4. So my result is negative 2, negative 4. And again, to remember how we multiply, I'm essentially thinking of 4, 1 as a column. So 4 times 0, 1 times negative 2. And then I do the same thing with 5, 2. So 5 times 0, 2 times negative 2. That's where those values came from, in case you have forgotten how to multiply them. AB2, I'm going to do it the same way. So 4 times 1 is 4, plus 1 times 2 is 2. 5 times 1 is 5, plus 2 times 2 is 4. That gives me 6, 9. And then 4 times 3 is 12. 1 times 0 is 0. 5 times 3 is 15. 2 times 0 is 0. That gives me 12, 15. So what is my result? My result is that I need to write each column vector that I came up with. -2, -4, which was my AB1. AB2 is 6, 9. And AB3 is 12, 15. We have talked before about the row column rule, but we didn't actually formalize anything, and so I'd like to formalize it just a little bit more this time through. So previously, I believe it was section 1.4 in your text where we looked at it when we were computing AX. And when we were doing this before, again, A was just one row. A was never more than one row, and so when we were multiplying, the values of A really turned out to be scalars. But now I want to look at the row column rule for when A is not just one row and B is not just one column. So obviously dealing with matrices as opposed to just vectors. And this rule says if the product AB is defined, and all this means is check your rows and columns that we've been talking about and make sure we can actually multiply the values together. For instance, if I said take B times A, hopefully you would tell me that you cannot, because B is 2 by 3 and A is 2 by 2, and if you'll recall, these two have to match up and they don't. So I cannot multiply B times A. But obviously I can multiply A times B because I've already done it. So let's continue with the definition. It says the entry in row I and column J of AB, and AB is just that product vector, is the sum of the products in the corresponding entries from row I of A and column J of B. And then it goes on to write this, and that's the formal notation. So that's a lot of words, but let's see if we can make that, again, make sense to us. So I went ahead and took the same A and B from our last example, and I also just copied over that solution that we came up with using the previous way that we multiplied. So not the row column rule, but the previous way where we took A times each column vector in B. And let's just see if we can simplify it and come up with the same result. So what this is telling me is that if I want to find AB11, so again, we already know this is going to be a 2 by 3 matrix for our solution, and AB11 would be my first row and my first column. So essentially I'm saying if I want to find that very, very first value, what am I going to do? Well, let me write this over here instead so we've got a little bit of room. AB11, according to this, tells me I'm going to take A11, B11, plus A12 plus B21. So what does this mean? A11 is 4, B11 is 0, A12, first row, second column, is 1, B21, second row, first column, is -2. So that gives me 4 times 0, or 0, plus 1 times -2, which is -2, and that gives me my result of -2. So good, this works. That gave us the right solution. Are you convinced? Again, what did that what actually happened is I'm looking at this row times this column. So this is exactly what we did in our previous example. And I'm taking the first entry times the first entry and the second entry times the second entry. And that's all this row column rule is saying. So let's do one more example just so that we're all satisfied and agree, and then we won't continue through that whole example since we already know the answer. So let's do this little guy right here. We know the solution already is 9. So this would be AB 2 because it's the second row and 2 because it's the second column. So what am I going to do according to my definition? A 2 1, B 1 2 plus A 2 2, B 2 2. A 2 1, let me get rid of all this other stuff here. A 2 1 is 5. B 1 2 is 1. A 2 2 is 2. It's a lot of 2's. And B 2 2 is 2. So what does that give me? 5 plus 4, which is 9. So I'm pretty satisfied. I know that this is already the correct answer, but I have verified 2 entries of my 6 using this row column rule. And again, just keep in mind that this is I1 and 1j, and this is I2 and 2j. So these values are going to be the same because obviously it's very easy to mess that up. Here's a practice for you to try on your own. So if you would, press pause, try this question in both ways using the definition and also the row column rule. And once you've tried it both ways and of course verify that your results match, then press play to see how you did. So again, the first thing I would do is note that A is a 3 by 2 matrix and B is a 2 by 2 matrix, and therefore they can be multiplied and the result will be a 3 by 2 matrix, which is always good to know as you get started. So I'm going to start with the definition first, and the definition tells me that I'm going to have A times B1 and A times B2. And so that tells me A, which is negative 2, 4, 1, 0, 3, negative 1, times the first column of B, and negative 2, 4, 1, 0, 3, negative 1, times the second column of B. Now this notation is just a little bit different than our the last time I did a question like this, because before I found AB1 and found the result, and then I did AB2 and found the result, and then I just put them together at the end. Notice here I have my first column of my vector is actually 2 other matrix and a vector, and then of course my second column of my solution is a matrix and a vector. So that can be a little bit confusing, and if you don't like that, that's okay. You can do it the way I did it before. So next thing I'm going to do is actually do the math. So I'm going to start with, and I should have used different colors here, but we'll start with this guy. So again, I will start by saying negative 2 times 5 plus 4 times negative 1. I'm not loving purple. It's a little bit dark. I'm going to try it again. We're just going to use white. So again, negative 2 times 5, 4 times negative 1. And then next, whoa, whoopsies. Next row would be 1 times 5, and 0 times, well, anything is 0. And then 3 times 5 is 15. Negative 1 times negative 1 is positive 1. So that is my first column. I'm going to put those back so it doesn't get confusing. And then I'll just use blue for the next one. And again, I'm doing the same thing. Did I lose a number? Oh, no, I didn't. So negative 2 times 0 is 0. 4 times 3 is 12. And then the first one's just going to be 0 on all of these. 0 times 3 is 0. And then 3 times 0 is 0. Negative 1 times 3 is negative 3. So my resulting matrix is negative 10 plus negative 4, 5 plus 0, 15 plus 1, 0 plus 12, 0 plus 0, 0 plus negative 3. That's my result, which is a 3 by 2 matrix. Now let's do this using the row-column rule. The row-column rule is hopefully going to give us the exact same result, and I'll probably end up with something that looks just like this, and then a solution. But let's go ahead and test it out. So I've got negative 2, 4, 1, 0, 3, negative 1, multiplied by 5, negative 1, 0, 3. And remember, all I'm doing is taking my first row times the first column. And remember, this is going to be a 3 by 2 matrix, so a lot of times people like to, I'm sorry, a 2 by 3 matrix. 3 by 2, good God. Let me just, let's start that one over. So 3 by 2 matrix, I was right the first time, I was just writing my little squigglies wrong. So negative 2 times 5 is negative 10. 4 times negative 1 is negative 4. And that was first row times first column, and notice that's where my results went, is the first row and first column. And now I'm taking my first row times my second column, so negative 2 times 0, 4 times 3. And notice I took first row times second column, and it went in my first row and second column. And then I'm going to continue with my next row. 1 times 5 is 5 plus 0. And then 1 times 0 is 0 plus 0. And then my last row, 3 times 5 is 15. Negative 1 times negative 1 is positive 1. And then 3 times 0 is 0. Negative 1 times 3 is negative 3. And then my result is, of course, negative 14, 5, 16. 12, 0, negative 3. And I got the same thing both times, so I feel pretty good about myself. Here are a few more properties for us, and I'm not going to go through any proofs for any of these properties. Again, they're fairly straightforward. The first one would require a proof, and your textbook goes through that, so I'm not going to. But essentially, this is the associative property for multiplication. The second is the distributive property, as is the third. And the fourth one really doesn't have a name, but what we're looking at is we have a scalar of r, and we're multiplying it by the product of a times b. And we're saying we can, instead of multiplying a times b and then taking it times that scalar, multiply that scalar by either a or b, and then multiply it by the remaining matrix. And the last one is the identity property. And again, that's going to come into play a little bit more in our next section. But the key here is we are dealing with an m by n matrix. And so I just want to point out that this would be the identity matrix M, which means we're simply using that so that the rows and columns works out so that we can in fact multiply. So if I'm taking the identity M times A, which is an M by N matrix, then I is of course M by M, and A is M by N, and that is why that works. And the same thing happens here. If I'm taking A, which is M by N, then when I take it times the identity matrix, it has to be the N by N identity matrix in order for that to work. So again, we know the identity matrix looks like this for however many rows and columns that we have. And I'm not going to do all of it, but we get the idea. We've got lots and lots of dots. And it is a diagonal matrix with ones in the diagonal and zeros everywhere else. So again, those are some properties to keep in mind moving forward. And a few other things to keep in mind moving forward are these warnings. So in general, AB is not equal to BA. Now we've talked about that a lot. And again, the purpose or the reasoning behind that is that we know that, say, A is a 4 by 7 matrix and B is a 7 by 2 matrix. Well, then my resulting AB is going to, because 7 is equal to 7, is going to be a 4 by 2 matrix. Whereas BA would not be a matrix that we could find, because B is 2 by 7 and A is 4 by 7. I'm sorry, that was wrong. B is 7 by 2 and A is 4 by 7, and 2 is not the same as 4, and therefore BA is not a valid product, and again, AB is not equal to BA. So that one's pretty straightforward. Number 2, or the second one, is if AB equals AC, it's not required that B is equal to C. And I'll let you kind of noodle on that one on your own, but exercise 10 in your textbook is a good example of that, and I may even assign that for your homework. And lastly, if AB equals 0, we cannot conclude that either A is the zero matrix or B is the zero matrix. And again, you can see exercise 12 in your textbook for a good example of that one. The transpose of a matrix is something we've probably never heard before, but the definition of a transpose says if we have a m by n matrix A, so A is m by n, the transpose, denoted AT, is an n by m matrix whose columns are formed by the rows of A. So let's make up an A real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So A is now a 3 by 4 matrix. The transpose of A is going to be a 4 by 3 matrix, and I'm going to take my first row, 1, 2, 3, 4, and make that my first column, 1, 2, 3, 4. My second row, 5, 6, 7, 8, now becomes my second column, 5, 6, 7, 8, and my third row becomes my third column. So that is what a transpose is. And you might be thinking, why do I need to know what a transpose is? Well, I'm going to tell you, but not today. So for now, just know that that is what a transpose is, and we're going to talk quickly about the properties of those before in the next section when we actually have to use transpose. Let's take a look at a few properties of the transpose matrix. The first property says that if I take the transpose of A and then the transpose of the transpose, I end up back at A. And we can work through this one fairly easily. Let's say I've got some value in A that's in row I, column J. If I take the transpose of that, then a row becomes a column and a column becomes a row, and that means that entry is now in row J, column I. And then if I take the transpose of that, it means that entry is now in row I, column J, which is, of course, back where I started. So that's okay with me. The second property says I can take the sum of two matrices and then take the transpose of that sum, or I can take the transpose of each matrix and then find the sum. And again, we should be able to think through this one pretty easily. I can either add the values together, then turn rows to columns and columns to rows, or I can turn rows to columns and columns to rows and then add the values together, and it's really not going to make a difference. So let's say I've got 1, 2 plus 3, 4, which is pretty easy to find the sum of, which of course is 4, 6. So this property says, hey, I can either turn this into my row into a column and my row into a column, which would of course give me 4, 6, or I can add them together first, which I already did, and then do the transpose of that, which of course gives me 4, 6. So pretty straightforward. And again, this is not a proof. You can't do a proof by just showing an example of how it works. You'd have to actually do a formal proof. I'm just showing you that these are in fact valid properties. The next property says if you have a scalar times a matrix and then you take the transpose, it's the same as taking the transpose and then taking it times a scalar. So for instance, I've got my 1, 2. Let's say I've got a scalar of 3. So this is saying I can take 3 times a, which would give me 3, 6. And then the transpose of that would be obviously in a row instead of a column. Conversely, if I take 3 times the transpose of 1, 2, which is 1, 2 as a row instead of a column, I am going to end up with, yes, 3, 6. So again, those are very simple elementary examples just to show you that those properties hold. The last one is the hardest one to understand. And again, we're saying if I take A times B and then the transpose, it's the same as taking B transpose times A transpose. And again, that's just all about the numbers, making the numbers work so that we can actually multiply. Let's say A is a 4 by 2 and B is a 2 by 6. Well, these two can be multiplied because my 2's match up, and my result, AB, is going to be a 4 by 6, which means the transpose of that would be 6 by 4. So then it makes sense that B, which was a 2 by 6, B transpose is going to be 6 by 2, and A transpose, because A is 4 by 2, so A transpose is 2 by 4. And so it makes sense now why we would have to switch the order, because if we don't switch the order, then we wouldn't actually be able to multiply the resulting matrices.